Hey everyone, and welcome. I am absolutely thrilled to guide you through today's explainer. We're going to unpack the hidden machinery that literally powers our modern industrial world. Seriously, it's spinning right now. In factories, inside water pumps, ventilation systems, and places you'd probably never even think to look. Today, we're decoding the ultimate invisible workhorse, the three-phase induction motor.
Okay, let's dive right into this. 80%. Just let that sink in for a second. It's a completely staggering fact that almost 80% of all industrial mechanical power relies entirely on this single invention. Crazy, right? Every time you see a massive conveyor belt moving or a heavy-duty crane lifting a crazy heavy load, there is an overwhelming probability that a three-phase induction motor is the muscle behind the whole shebang. But why? How did one specific machine come to completely dominate the globe? Well, to answer that, we kind of have to travel back a bit. All the way back in 1887, Nikola Tesla actually invented the very first AC induction motor. And what he gave us was a technological marvel that's surprisingly simple, incredibly rugged, and just exceptionally reliable. Unlike older motors, it doesn't rely on a complicated, high-maintenance series of sparking mechanical contacts to spin. Nope. Instead, it relies on the elegant, completely invisible rules of electromagnetism. It's an invention that has quite literally been transforming our world ever since it first sparked to life.
Moving on to section 1, we'll look at the anatomy, specifically the stator and the rotor.
To really grasp how this thing works, we need to basically take the machine apart and peer inside the casing. An induction motor primarily consists of two main parts. On one side, we have the stator, and as the name beautifully implies, it's completely stationary. It's the outer shell that receives the three-phase electrical supply straight from the power grid. Then, nestled right inside of it, with just an incredibly tiny air gap of sometimes less than a single millimeter, is the rotor. This is the spinning inner core that's physically connected to the mechanical shaft. So the stator takes in the electricity and the rotor outputs the mechanical work. Pretty elegant, right? Let's see how this plays out when we look specifically at the rotors, because there are actually two main types here. First up, we've got the squirrel cage rotor. It actually gets its name because its conductive bars form a cylinder that looks exactly like a pet hamster or squirrel wheel. It's simple, it's rugged, and the bars are permanently short-circuited. Because of this basically bulletproof design, it commands about 90% of all industry usage. Now compare that to the slip ring or wound rotor. This one's a lot more complicated. It has actual windings, slip rings, and brushes. And while it needs way more maintenance and is rarely used, making up only about 10% of the market, it has a serious superpower. You can add external resistance to it, which grants it absolutely massive starting torque for moving really stubborn loads like heavy cranes. All right, section 2, the physics. The rotating magnetic field. So how in the world do we get that rotor to spin without any physical electrical connection to it? Well, the secret sauce here is the rotating magnetic field, or RMF for short. Remember, the stator is entirely stationary, nothing physically moves. But because we feed it a balanced three-phase electrical supply, where three distinct alternating currents peak sequentially exactly 120 degrees apart, the combined magnetic flux does something, frankly, pretty magical. Through the vector addition of those three phases, the resulting magnetic field maintains a constant, super stable amplitude of 1.5 times the maximum flux of a single phase. But here's the kicker. Its axis continuously shifts in space. So the windings just sit there, totally still, but the magnetic field they project is spinning furiously in circles. Let's actually walk step by step through the resulting domino effect of this electromagnetic induction. Step 1. That balanced supply creates our spinning magnetic field. Step 2. As that invisible magnetic field sweeps around, it physically cuts through the stationary conductive bars of the rotor. Step 3, according to Faraday's law of induction, this cutting action induces an electromagnetic force, or voltage, directly into the rotor. And since the rotor is a closed circuit, a massive current suddenly begins to flow within it. Finally, step 4, this newly induced rotor current creates its very own magnetic field, which then reacts against the original stator field. The result? A mechanical force is applied to the rotor, torque is produced, and the motor just begins to spin. It is entirely self-starting. How cool is that? Moving right along to section 3, chasing speed, understanding slip. There is a really fascinating irony to how this motor operates. It's essentially engaged in a never-ending chase. We call this chase slip. Slip is simply the difference between the synchronous speed, that's the blazing fast speed of the invisible rotating magnetic field, and the actual physical speed of the spinning rotor. The absolutely crucial point here is that the rotor never quite catches up to the magnetic field. It absolutely must always lag slightly behind. Why? Because if they were moving at the exact same speed, there'd be no relative motion. The magnetic field lines just wouldn't be cutting those rotor bars anymore. And this leads us to a truly brilliant paradox. If the slip ever reached exactly 0%, meaning the physical rotor somehow perfectly caught up to the speed of the magnetic field, there would be zero induced voltage. No induced voltage means no rotor current. And without rotor current, there's absolutely no torque. The torque would immediately drop to zero, and the motor would stop spinning until it slowed down enough for the magnetic field to start cutting those bars all over again. It's this beautifully self-regulating system that's completely driven by its own constant slight imperfection. All right, section 4, taming the motor. Starters.
Now, actually starting these powerful machines introduces some explosive, potentially hazardous challenges. At startup, the physical rotor is entirely stationary, meaning our slip is at its absolute maximum of 100%, or unity. Because the relative difference in speed between the stationary rotor and that lightning-fast magnetic field is so huge right at the beginning, a massive voltage gets induced. Because of this, an induction motor can draw a dangerous 6 to 8 times its normal full-load current just to get moving. If you actually try to start a massive industrial motor directly from the grid without any protection, that sudden massive draw of current would cause voltage drops so severe it could literally collapse the entire local electrical system.
So, to avoid shutting down the grid, engineers have developed some incredibly ingenious hardware solutions to safely spool these beasts up. Let's look at the most common types of starters used to limit that massive current draw. First, stator resistance and auto-transformer starters work by temporarily dropping the voltage supplied to the motor during startup. Then you have the star-delta starter, which cleverly reconfigures the wiring on the fly. It starts the machine in a lower voltage star configuration before seamlessly switching to delta once it's up to speed. For tiny motors, under 5 horsepower, a direct online, or DOL, starter is completely fine, mostly just acting as basic overload protection. And finally, for those complex slip-ring motors we discussed earlier, we use a rotor resistance starter. This lets us add electrical resistance directly into the rotor circuit, vastly dropping the current, while simultaneously boosting that crucial starting torque. Finally, we arrive at section 5, quirks, cogging and crawling.
Even the most advanced industrial machines can sometimes act a bit, stubborn or clumsy. Let's start with crawling. Sometimes, due to odd magnetic harmonics, specifically the 7th harmonic playing weird little tricks in the tiny air gap, the motor just gets confused. It moves sluggishly, getting stuck at exactly 1/7 of its intended speed. It literally just crawls along. Then there's cogging. This is a stubborn, complete magnetic lockup. If a motor is poorly designed so that the number of metal teeth or slots on the stator perfectly equals the number of slots on the rotor, they can magnetically lock together. When you apply power, instead of spinning smoothly, the machine just gives you angry, jerky movements, or it just outright refuses to budge at all. We've covered so much today: the brilliant design, the invisible physics, the paradox of slip, and the sheer raw power of the 3-phase induction motor. But I want to leave you with this final provocative thought. With a staggering 80% of our world's industrial mechanical power relying on these exact motors, how will future engineering innovations perfectly optimize magnetic geometries to permanently eliminate those clumsy quirks of cogging and crawling? It is an absolutely incredible engineering challenge for a machine that we literally cannot live without. Thank you so much for joining me on this explainer. Keep learning, keep exploring, and I'll catch you in the next one.